All right, let's see. So we didn't get to finish, I think on Thursday, I was trying to introduce 12.3, but we didn't have time. So let me go back to the notes here. There they go. Okay. So before we jump in, I just have some comments to kind of like help remind you guys what we were doing last week to connecting it to this week. So I have a little warm-up comments here before we jump into the section. And so we were looking at vectors. Let's see, where are they? We were looking at vectors. That's what we started with. That's what we covered in 12.2. So unlike vectors, though, we're going to be doing all kinds of operations in the next few days. Sorry, unlike real numbers, vectors have different kinds of multiplication. Different kinds of multiplication. So I kind of want to show you what that's going to look like before we jump into it. There's going to be all kinds of weird notation. So let's do number multiplication. And let's look at the kinds of notation that you're going to do for vector multiplication. Okay. So let's say we have two numbers. Let's say we call them 2 and 3. So let's say 2. If I wanted to multiply 2 and 3, what are different ways? Like, what are different notation that you guys can use to portray 2 times 3? The little cross X, right? So I think in elementary school you learned this one. You learned the dot. So this is the same thing as the dot. What else? How else have you written? Parentheses. And you've also written it like that, right? Is there another one? The cross one. Which one? I guess when we're using numbers, I think that's the only one, right? Now, if we use variables, if you use variables to represent numbers, you've also been writing it like this. But how else do we write it? Just put it next to each other, right? So all of these different ways of writing multiplication all mean the same thing. 2 times 3 or 6 times 3. But for vectors, that's not going to be necessarily true. Okay. So when I put C times, let's say, V, this is the one we did last class. We called it scalar multiplication, right? So this was called, in the green, this was called scalar multiplication. And it was a certain process of doing this. It was, you guys were telling me it stretches the vector, right? Here, what is C? It's a number, right? Which we're calling a scalar. And V is a vector, okay? Now, in these next two sections, the notation we're going to use is we're going to do a vector multiplying with another vector, but in one, we're going to use the dot. And then in another one, we're going to use the cross. And as you can tell from their name, one's called dot product, one's called cross product. So this one here is going to be called dot product. And so dot product. And this one's going to be called cross product. And if you guys look at your notes from Thursday, when you multiplied a scalar with a vector, was the result a number or was the result just another vector? It was another vector that was like scaled, right? It was like stretched. So this gave you a vector. Okay. What we're going to learn today is that the dot product, when you multiply two vectors, they're going to give you a number. They're going to produce a number. Yep.
Just like the numbers not.
The number is not a vector here. We're calling it a scalar.
So it doesn't represent the coordinates? Or-
It doesn't represent like coordinates on, yeah, it doesn't represent anything it doesn't represent something that has direction and magnitude. It's just like, it's just gonna represent like a real number. That's it, standalone. And you'll see how that works out. The cross product is going to produce another vector. Okay, so here, the reason I'm explaining this here is because here, when you guys have multiplied two numbers together, the result is just another number. But here, depending on the type of multiplication you do, sometimes the result is a vector, sometimes the result will be a number. Okay, so you writing dots is going to mean something totally different if you write cross, and we're going to see that. Versus in real number multiplication, it doesn't matter which one you use; they both mean the same. Okay, so that's just kind of like a notation remark. So move the camera just a little bit.
Yeah, question. Which one really includes like using the parentheses instead of?
It'll be a dance between these. So for example, like if I want to do a one with parentheses, we're gonna see that I could do something like this. 3 times V cross VW. If in this case, I'm using parentheses to differentiate what products do first. But we don't have notation for something like this, where it's a vector, parenthesis, a vector. There's no notation. Okay, so let's see exactly how this is going to look. So this is the dot product. Dang it, I keep wanting to write, my brain wants to write drop in the way. Dot product, okay. Let's see here. So let's see what this is going to look like. Let's define the dot product. So we're going to say for vectors V, and we're going to write it as a position vector. V1, V2, V3, and W, W1, W2, and W3. The dot product V dotted W is defined as, and this is how we're going to do it. Okay, so if I take the dot product of these two things, remember how when we did a scalar and we multiplied it with this vector, that scalar was multiplied to each of the components? Okay, so what we're going to do here is we're going to multiply the components of V with the components of W. We're going to do the first component times the first component of W, so it'll be like this. It'll equal V1 times W1 plus, and then you do it for the second component. Then you add that product, W2, and then you multiply the third component. That's how we're going to define the dot. And we're going to see, right now we're just kind of introducing it, we're going to see that this number is going to give you some information about this two vector. Okay? So let's take a look at just a concrete example. Give me a random vector, three-dimensional vector. 1, 2, 3. 1, 2, 3, all right. Give me another one that has maybe a negative in it. If you choose negative 3, negative 5. Let's make that one positive. Just so that very still there. That okay. And so this tells us that when I take the dot product of these two vectors, I multiply the first component with this first component of the second vector. So it's 1 times -2 plus 2 times -3 plus 3 times 5. Which is gonna give you -2 minus 6 plus 15. What is that? 7? 7. And so the dot product of these two vectors, for some reason, will give us 7. Right now, it seems very arbitrary, but we're gonna see 7 next. Has to do, there's some connection. Here. So right now, when I'm going over, guys, in the notes, was at the end of Thursday's notes that we didn't get to cover. So that's the part that you'll see this in the end of Thursday's notes. So let me, with your classmates, let me have you guys just do like a little discussion here. Which result do you think is a scalar, a vector, or undefined? So let me give you four different types of operations here that now kind of like they're playing with each other using notation that we've discussed up to now. Okay, so the first one will look like this: A dotted with B parentheses C. The second one is A dotted with B and then dotted with C. Then we got magnitude of A parentheses B dotted with C. And then we have magnitude of A parentheses B plus C. And so let's say you knew vectors B, let's say you knew vectors A, B, and C. And from your understanding of the notation that we've learned so far, I want you guys with your classmates, maybe group up with the same groups from last week and discuss, should the result of this be a vector, a scalar, or is it undefined according to what the definitions we have up to now? Okay? So I have you guys three here to discuss. You three here to discuss. You guys across can discuss here. Okay? I think the usual here, right across from each other. I have you two guys. You guys here can work. You three here, and then you two guys. Okay, so with your classmate, decide what should these equal.
That's the same as
Yes. Yeah. I'll make a comment. There is. So if they write this on the textbook,
Yeah, like that, or without.
what you need to do is, you need to know is the thing inside. Oh, they don't even have an arrow. It's bolded, right? Well, hold on. Actually, we do it this way. Well,
I don't know if there was. I don't think there are any.
like that, on a textbook.
Yeah, that would just be.
So the textbook bolds the letters to represent vectors. If it's not bolded, then it's a scalar. So in the textbook, yeah, I don't really like that as well. You need to know that if the thing inside is a scalar, this is an absolute value. But if the thing inside is a vector, then it's really magnitude. Yeah. Yeah, yeah.
It wasn't actually, but like the A referring to the.
If the thing inside is a vector, then yeah, this represents magnitude. Yeah. Yep. All right, guys, I forgot my flashcard. So let's see. Someone from this row. What did you guys get for number 1? You guys got vector? Okay. Let's see. You got vector. What did you guys say this thing inside was? The result of this would be a what? A scalar. Because when you take the dot product, you're just going to get a number, right? Okay. And this scalar is doing what kind of multiplication with C? Yeah. Yeah. So what you have here is you have a scalar multiplying with a vector, and that we define to be scalar multiplication, which produces a vector. Okay. All right. Let's see. Someone from this row. I'll pick you guys right here. What did you guys say for the second one? You saying undefined? Okay, let's see. Undefined. Let's see. This we said already was a scalar. And then this here is going to be a what? Like that. Now, either if I use the dot, here's where you got to be careful. If I'm using a dot, either the two things are numbers, scalars, to give me a scalar, or the two things are vectors to give me a number. But we don't have a definition of a scalar dotted with a vector. That right there is undefined. You can see the difference? Okay. If I would have done this, then it would have been a scalar time dotted with a scalar, and it would have been talking about this kind of product. So then it would have been a scalar times a scalar equals a scalar. Okay. So this is why I'm kind of having this part. The textbook doesn't discuss this that much, but like the notation will really matter here, depending on the operation. All right, let's see. You guys here. What did you say for the third one? Scalar? Okay, let's see. So scalar. So this is a vector with a vector, so that gives you a scalar. And then the magnitude of a vector is a scalar, right? And so what kind of product is that one? It's going to be something like, I think like this one, right? A scalar, parentheses, a scalar means times a scalar. So correct? And then the last row, what did you guys say for that one? What did you say? Vector. Okay, let's see. So vector. Let's see. So a vector plus a vector produces what? Another vector, right? That's what we did last week. So it produces another vector. And then this is the magnitude of a vector is a scalar. Good. And so then what kind of product is this? A scalar next to a vector is scalar multiplication. So it'll produce a vector. Good. So yes, good job, guys. And then more gets added to the list. Okay. Right now we just have, that's all we have for now, but more will get added to the list. Any questions on those? Yeah.
Is number two undefined just for now, because we don't know how to like dot product with scalar, or is it always like that?
It's gonna be undefined. Yeah, we won't define an operation with a dot that uses a scalar and a vector. And then one of your classmates had a question about the textbook. So the textbook doesn't use like a double absolute value for magnitude. They just use two vertical lines. And they don't use the little arrow notation. I think they just bold it, don't they? They just bold it in the textbook. So when you're reading the textbook and you just see something being in these two vertical lines, if the letter inside is bolded, then it's a vector. And therefore, these two vertical lines mean what? Magnitude. Right. So in this case, this is talking about magnitude of vector A. But if the letter inside is not bolded and you're told it's a scalar, then now these vertical lines mean what? It means absolute value, correct, of the number A. Okay? So just some notation stuff. Yeah, that's like the one thing I don't like about the textbook with this class is that they don't use the bars like that, and they don't use a little arrow here. But it's all good. I give you that heads up. All right, guys, good. Now, if you're taking physics, or at some point if you do end up taking physics, the dot product is used up. And I want to give you guys a little application example of that. So here's an example when it comes to physics and kind of how it's used outside of like the math class. So in physics, you guys can help me here. Work, what is it that you guys have been, when you're trying to find work, what is it that you do? What operation is it? Force times displacement, right? So you normally do the force on an object, and then you multiply it by the displacement of the object. Displacement of the object. And usually we call it F, and then what letter? Is it just lowercase d? Or delta? Yeah. Delta, okay. I'm gonna keep it d for this, just because it'll match up with what we're doing. Okay? But as long as you understand that that's the displacement, like how much the object moves. So now we take that, and usually in the physics class, it's 2D, meaning you're just looking at how things are moving sideways, diagonally. There's not really depth yet, unless you're at that point in the physics class. So at some point there will be depth, and you will be dealing with 3 dimensions. And let's say the object is right here. Say it's like, I don't know, some square object here. And there's force that acts on it, and it ends up moving over here. Okay? Moves over here. So it starts here and it goes here. And let's say the force acting on it is going in this direction. So now you're going to have a vector representing the force vector. I think I mentioned that last week, where the first component is how much force is being applied in the x direction, then how much force is being applied in the y direction, and the force being applied in the z direction. And then you're going to have your displacement vector. That displacement vector, when the object is here, it moved to another point in space. So it moved a certain number of x units, a certain number of y units, and so on. So the displacement now, there's 3 kinds of displacement. The displacement in the x direction, the displacement in the y direction, and the displacement in the z direction. And so now, when you're gonna try to find the work applied on this object here, you need to take into account how much work happened in the X direction, how much work happened in the Y and on the Z. You see that? Okay. So then in this case, the total work that you're gonna compute. How would I calculate how much work happened in the X direction? How much force happened in the X direction, right? Times how much displacement in the X direction. So then we multiply F1 with D1. And then what do you think we do? And then you add them up. Yeah. So then you say how much force, how much work in the Y direction. So F2 D2, and then F3 D3 to give you how much work in the Z direction. But in terms of vectors, you guys see how their components are being multiplied and added? That looks very similar to this. So then in this case, the work turns out to be the dot product of the force vector with the displacement vector. And so that's how you're going to do it. That'll give you the total work. And so here's an example in your physics class where they're going to use this operation. Okay. And then everything we're going to discuss today about dot products, there's going to be all kinds of geometry stuff that we're going to discuss, will then apply to the geometry of the force vector and the displacement. It's going to be pretty dope. I can't tell if you guys are like so pumped that you're like just dying inside and quietly feeling it, or you're like, move on, bro. I'm going to assume the first one, just from what I've been reading in the math autobiography, which have been great, by the way. Okay, so here's just an example to kind of show you why we're learning all this stuff. If you're going down a more engineer path, questions on that? Yeah.
If the force is that way, how's the displacement that way?
Well, remember, I'm drawing this like on 2D. So this force could, for example, be coming this way. Yeah, and so the object, I don't know, let's say this is being pushed this way, and then it's being not necessarily dragged this way, but like maybe this way. Yeah, so I'm drawing like a 3-dimensional 2D, so it gets a little distorted. Yeah.
So the force and the displacement are like almost unrelated.
Not quite. We're gonna see in a little bit that the direct, like there's this angle in between them. And the angle in between them, we're gonna see, for example, we're gonna see that if the displacement, I want the vector to move this way, right? Or the object to move this way, but if my force vector is completely perpendicular to that, then there's no way for me to move it like this. So that will result in work being 0 because nothing was really being done. And we're going to see how that happens. So there's going to be some relationship between the dot product and the relationship that the two vectors have in terms of like how they relate to each other in the direction that they're pointing. You had a question too. Okay. So there are some properties of dot product that we're going to use today, and then there's going to be sometimes proofs that we're going to look at that use these properties. Let's see, properties of dot products. So let's just define these things real quick. So let's let V, W, and U be vectors, and C a scalar. Let's just put some number. So here's a nice property that we're going to see a lot in this class. If you have a vector, let's say V, and I dot it with itself, right? I dot it with itself. Like, let's say I got this vector, V,
and I dotted it with itself. Then it would be D1 times D1, so D1 squared plus D2 squared plus D3 squared, right? Because it's just multiplying with itself. But then if we look at magnitude of a vector, it was this squared plus this squared plus this squared under the square root. So the relationship that it has with the magnitude of itself is that is its magnitude, but I square it so that the square root goes away. Okay. And so we're already seeing a connection, a geometrical connection that this has with the dot. It's the square of its distance.
You're saying the textbook that uses like absolute values.
Yeah, the textbook doesn't use two lines for magnitude. It uses just like, it looks like an absolute value. But what I was saying is that you as the reader need to understand on the textbook that if I really have a vector in here, it really means magnitude, not the absolute
Do
value.
you prefer the double lines?
Those are double lines when you're doing it by hand. Yeah. Double. Okay. Another property is that when I take two vectors and I dot them with each other, like I did here, notice that because multiplication is commutative, I can just swap the D1 and the F1, swap and swap. And so then that will produce a swap of the dot product. Okay. And so notice that it's commutative. Commutative. Okay. You can swap dot products. Here's another one that plays around with the parentheses that somebody was asking. If I have a vector and I dot it with the sum of two vectors. Is that the one I gave you guys? Oh, no. Notice the sum of two vectors is a vector again, and it's being dotted with another vector. So it's defined, right? So here it's kind of like distribution. Dot products, you can distribute a dot product. So it's V dotted with W plus V dotted, dotted with the second vector. You can distribute a dot product. The other one does like a little dance with scalar multiplication and dot product. So if I have a vector and I scale it by scalar multiplication, and then I dot it with a second vector W, it turns out that it's the same thing as if I scale the dot product of the two vectors, meaning I do the dot product first and then I multiply it by 6. Which it turns out is the same thing as if instead I would have scaled the second vector by that same scale. It's a little tricky. And then the last property is the zero vector. The zero vector dotted with any vector, what do you guys think will give you? Zero vector or the zero number? Number, because the result needs to be a scale. Zero number. Yeah, no, what's up?
These are like properties that we learned before in like, right? Like 3 is distributed and 4 is associated.
Yeah, exactly. Yeah, so they look very similar to like real number operations, but when we do cross product, these might not necessarily be true. So this kind of seems to behave like real number, like when you multiply by numbers, except that now that we have this weird thing here, but that's a little different because now let's talk about magnitude. Okay, but yeah, we'll see with like, for example, cross product, these might not be true. Okay, yeah.
So for number 4, if you have the one in the middle, the C multiplied, so you can't distribute that, otherwise it'll be like twice.
Exactly. Yeah, that's what you gotta be careful. Yeah, that's a good point. That's observational. That this, doing something like this is incorrect. You can't do that. Okay, yeah, because otherwise this would be false in this case. Yeah. Okay, so there's these 5 properties. And then there's another property which is so strong, it's actually a theorem. And this is the one that I've been telling you has a relationship between the directions of the vectors. And so to do that, we're going to put an angle in between the 2 vectors. So it says if theta is an angle between vectors v and w, where, and this part's important, guys, so let me pause for effect, where the angle between vectors is only going to be between 0 and 180 degrees. Okay, so when we're looking at angles between vectors in this class, we're not going to look at angles that are bigger than 180. So the most they can stretch is like this, where they go in opposite direction. If it keeps stretching, now theta is going to be the one down here. Okay? It'll always be between 0 and 180. So if that's the angle between them, then it turns out, and I'm going to just show you guys the proof here, that when you take the dot product of these 2 vectors, it's equal to the magnitude, the product of the magnitudes, sorry, put the right in there, times cosine of that angle. Pull that out, give me 1 second. Let me show you guys. Pictures for class, proofs. Smaller. Okay, and let me just demo. I just want to demonstrate. That way we're not writing the proof. I'm not trying to be on the proof or anything. But I just want to show it to you guys. Okay, so here's the proof of this guy here. It's pretty dope, but it definitely has you review a lot of geometry. Okay, so what we do is you get the 2 vectors, right? Put them in the origin here, they're position vectors. And then remember I told you guys that when they do the subtraction vector, they put the 2 initial points together. Remember we discussed that? But if I do A and then I negate B minus B, then it goes from here to here. Remember that? So from here to here is literally that vector as well. The difference vector. Okay, so from that we get a triangle. Okay, it's not necessarily, we don't know, we can't assume it's a right triangle. So because of that, we use the law of cosines, which says that if this is the angle theta we're considering, then the side opposite of it is what they're calling the vector AB. AB or BA, they'll both have the same magnitude. Okay, so that's the magnitude of this vector squared equals the sum of the squares of both of the 2 sides of the triangle. That's OA and OB right here, minus 2 times the product of those 2 sides. And then cosine of that angle. Does that kind of slowly ring a bell? If not, it's okay. Okay. But there was this law of cosines that you guys learned in trig that related the side opposite of an angle in this magnitude. Okay. They're saying for the extreme cases when theta is 0 or pi, then in that case, if it's 0, they're gonna be on top of each other. Okay, and they're saying it still will work, or the two vectors are just the 0. All right, here, let's see, let me go back up. They're just defining here, they're saying this magnitude is just the vector A, this magnitude is just the vector B, and then AB is the magnitude of the different vectors. So, remember, this means magnitude, right? So then now they're basically using the law of cosines that they did earlier, and they're just rewriting it in terms of A, B, and the different vectors. You guys can see that? Now this is where the dot product comes in because of I can't do it. Property number 1. A vector dotted with itself is its magnitude squared. Okay, so it says using properties 1 that we just wrote, properties 2, where it's commutative, and properties 3, which was the distribution, I believe, yeah, the distribution. If I dot this vector with itself, the difference vector, okay, notice that by definition, a vector dotted with itself is just its magnitude squared, right? So that equals this because of property 1, but then here they use property 3 to do distribution. They distribute, blah, 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 like this. And then they use property number 2 to say it's commutative. A dot B is the same thing as B dot A. So these are the same thing. So there's 2 copies of those. And so then they are able to rewrite this in terms of this method. And so then they're saying, therefore, the left side of this equation that use law of cosines can be replaced with this whole expression. And that's what they do with that. So then they do a little algebra. These are now just numbers. These are all just scalars. So boom, cross out the a squared, cross out the b squares, and now you're left with this bad boy here. Divide by -2, and then you get the result of the thing. And then see that little square that I told you guys? There's a little square. Okay. So that's just a little just wanted to show you guys that. It's always nice to see the proof. Okay. So now one question is, why the hell would I want to do the dot product this way? When it's hella easy to do it, I just multiply the components, right? So this theorem is not so much used to compute the dot product, it's used to find the angle theta of the angles. Oh, sorry, between the vectors. That's how you're most likely going to use this stuff. And so we use this theorem to help us find the angle between two vectors. The angle between two vectors. And we do that by, since these are just scalars of magnitudes, we divide them off, and we can rewrite this theorem equation as the dot product of two vectors divided by their magnitude. Assuming none of those are the zero vector. So that we're not dividing by 0. So let me have you guys try doing this real quick. I'll walk around and help you out. So what I would like you guys to do is find the angle between I hat and J hat. No, that's too easy. I hat and the vector 1, 1, 1. There you go. That's what I meant. And then here, I'll draw it for you guys. So remember, I hat was which vector? It was this one of the standard basis vectors, 1, 0, 0. So it'll be right here. This is I hat. And then 1, 1, 1 goes 1 to X, 1 towards Y, and then 1 up towards Z. So then it looks like this. But shooting out like towards you guys. And so what you guys are doing is you're looking for this angle theta right there. Okay. Try to use this stuff. Try to use this. We're gonna do it using the dot product. I will tell you now, it's not one of those special, yeah, 30, 60, none of those. Do it in degrees. Do it in degrees. I had dotted V and then use their components to do the dot product.
It's gonna be a square. Square root of 1 squared, not 1 squared. Should, it's. That's right. So it'll be, so then split up. It'll just be one. On that side. Wait, no. Yeah. Yeah.
If you finish before your group, just check in with them, try to help them out. Help each other out, guys.
So, yeah. So it's the 92, I have a good one, so you want to.
So then,
Yeah.
yeah, let's go ahead. Try to find the angle in degrees.
Yeah, because you've got one on top. What you don't do is a little bigger stuff.
I know, it's weird, I wrote there, I mean, you have to do like the whole, like, it's kind of the.
Wow. Wait, you don't have to.
No, well, they didn't let us know until that.
Oh.
Yeah, no, like, yeah, you're right, text, like that.
All right, guys, let's see what's up. Let's see what's up, guys. So let's try to use this our theorem here. We know we're gonna have. What did you guys write here? We cosine of what? What goes on the top? A one, what did you do though to get that one?
Multiply 1 0 0 by 1 1 1.
And then now how did you use the vector? You bring the dot product. Good. Oops. W, it's what is it? V. And then on the bottom, you multiply them by their magnitudes. The magnitude of this, magnitude of this one. So you got cosine theta is 1 times 1 and 0, right? And 0 and all that. So then this just gave you 1 plus 0 plus 0, which was just good old 1. And then what was the magnitude of I? Was 1. What was the magnitude of V? Root 3. 1 plus 1 plus 1. So it's just 1 over root 3. And unfortunately, that one is not, it doesn't correspond to a special angle, so you do have to use your calculator. The cosine inverse of that. And what did you guys get on your calculator?
54.7.
54.7. There we go. Nice. So that's the angle between those two vectors, okay? All right, sweet. So I just wanted you guys to kind of get practice on how you actually use that theorem to help you find the angles. And now we're going to take that and go a little bit further with it. So let's see in general, let's try to find some relationship now that you kind of have an idea of how this works. So let's use you guys. I know a lot of you guys mentioned you love trigonometry. Let's use trigonometry to conclude some remarks. This is that good old unit circle. This little unit circle. That. You got your radius being rotated by some angle theta. And what did we say was the x coordinate on the unit circle in relationship to theta? It was cosine of that theta, and the y coordinate was sine of that theta. That's if this is a unit circle. Cool. Okay. So what I want you guys to notice is when I do the dot product here, okay? Let's look at it here actually. Will the magnitude ever be no, let's look at it here. Will the magnitude of V ever be negative? No, because if we're thinking of it as length. So this will always be positive, and this will always be positive. So out of this, what controls whether the dot product will be positive or negative? The cosine of that angle, right? That's the only thing that will really tell you what's going to be, if it's going to be positive or negative. And let's use that fact with the unit circle that we know about cosine of an angle. And remember, it's only going to go from 0 to pi. So when you guys learn the unit circle, you guys learn, what was it called? All students take calculus. All students, meaning all the trig functions, sine, cosine, and tangent were positive. Then I told you which quadrant, which one was positive, which one was negative. Okay, but let's just focus on cosine. So Cosine can either be positive, it can be 0, or it can be negative. Okay? Can you guys tell me for which angles is cosine going to be positive? From what? From 0. If theta is from 0 to 90. Okay. Actually, does it include 90? No, right? So it just goes to positive 2. No. When is it 0? At 90, yep, at pi over 2. And so then when will it be negative? From 90, but not including it, to 180 pi. Right. From here to here, it's positive. Then cosine 0 here, because the x-coordinate is 0. And then the x-coordinate is negative here. Okay? But if we use this now, notice that when you do the dot product and you get a positive answer, you get a positive number, what does that tell you about the angle between the two vectors if you get a positive number? It's going to have to be less than 90, right? Because this will always be positive, this will always be positive. But if I get my answer positive, then cosine has to be positive. And that can only happen when the angle is less than 90 degrees. So for this situation, we know that the angle is going to be acute between two vectors, 90, less than 90 degrees. What must happen when the dot product is 0? What do the vectors look like? They have to be perpendicular, right? Because if the vectors are not the 0 vectors, the only way for them to be 0, the magnitudes won't be 0. The cosine value has to be 0. And that only happens when they're 90 degrees. So now this is telling you that when the angles are perpendicular to each other, that's going to happen when the dot product is actually giving you 0. And then if the dot product is negative, that happens because cosine is negative, which happens when the angle is bigger than 90, but less than 180. So it'll be obtuse. So that tells you that the vectors are like relative to each other, they're kind of pointing away from each other. Okay. Well, and so remember the first dot product we did? We got 7. If you guys look at your notes, the first dot product of those two vectors. What does that tell you about the two vectors if the dot product was 7? What's the angle between them? It's going to be less than 90 degrees. So they're relatively like pointing in the same direction. Maybe not exactly, but they're definitely not pointing in opposite directions. Okay, good. We're building some cool stuff up. And so we use this. We're gonna define a new term that you probably never heard, that we use a lot in the calculator class. We're gonna say two vectors are orthogonal if and only if the dot product of them is 0. Because that's the only one that really, this tells you that their angle is obtuse, but it doesn't really give you the angle. Well, this one for sure tells you the angle has to be 90 degrees. Okay. So I just have a little remark here, a little note. The word orthogonal here, orthogonal, is an algebraic, how do I say it here, property. What do I mean by that? It's telling you something about the way the dot product of the two vectors behave versus, actually listen to the verses. perpendicular is a geometric property. Okay? Is a geometric property. So from what we discussed, we're noticing that that one must happen and the other one's happen. Okay? Meaning if two vectors are perpendicular to each other, then their angle is 90 degrees. So then when I compute using this theorem, cosine of 90 degrees is 0, and so therefore the dot product has to be 0. Okay? If the vectors are orthogonal, then the dot product is 0. Okay? And so then when I use this here, the dot product is 0. So I'm going to get cosine of 0. But if the angle can only be between 0 and 180, what angle must that be? It would have to be pi over 2, 90 degrees. So therefore, it'll be perpendicular. Okay? So these two, sometimes people use them interchangeably, but just understand this is talking about the geometry of it, meaning the angle. This is talking about the dot product of the vectors. Okay? What time is it? All right. You want to take a break? Or you want to keep going for a little bit? I have parallel. I just want to talk about parallel, and that's it. All right, let's finish parallels. Since we're kind of on a roll. It's not that long. And then we'll take a break. Okay, so yeah, so this is talking about vectors being perpendicular to each other. It happens when their dot product is 0. So now the question is, how can we tell if two vectors are perpendicular? So, how can I tell if vectors are perpendicular? Sorry, parallel. Sorry. So first, let's kind of discuss what that means, because with lines, two lines were parallel when they weren't intersecting, right? But here vectors don't shoot on forever. So if I have two vectors, how can I point? I guess how can I point them so that they're parallel? What would have to happen? Think in terms of their angle. Yeah. They have to have the same direction. But for example, let's say this one's pointing this one's pointing. They look parallel here, right? Are these parallel?
Yes.
See, that's where it gets weird, right? Because lines don't really have direction, they just shoot both ways. But here vectors do have a starting point and an ending point. Okay. One way to help you out is let's pretend I have lines that shoot through the vectors. If I have a line shooting through this vector and a line shooting through this vector, will those lines be parallel? Did I draw them kind of parallel? Yeah. Okay. Yeah, right? But what if they're like that? And I shot a line through this vector and I shot a line through this vector. Will those lines also be parallel? Correct. So in this case, it seems to happen in two different scenarios.
Just absolute.
So you can absolute value. Oh, I see what you're saying. So get rid of the opposite sign.
Yes.
So yeah, but what we're gonna do instead is we're gonna use angles to help us out. Okay. When they were both pointing in the same direction, and I put them, let me make this one a little longer. And I put them on top of each other. What is the angle between them? 0. But if I go like this, and I put them, and I combine their initial points, now what's the angle between them? 180. And so that's how we're going to actually define parallel vectors, with angles. Okay. So we're going to say two vectors are parallel if the angle between them is either 0 or pi. And in this case, it's talking about them in radians. So let me put those two scenarios that I just described. Let's put them right here. So let's say it's 0. So here's V. And then I put W right on top of it. Versus here's V. And now it's 180, so it's pointing completely opposite. Okay. Here the angle theta is 0, but here the angle theta is pi. Instead of just telling you a property, I want you guys to help me see it. So here's V, right? What do you notice between the relationship of the direction and the magnitude of V and W? Direction-wise, the same. Magnitude-wise, they're different, but like by some scale, right? What did we do to vectors that did that? We did scalar multiplication, right? That scaled the vectors. So in this case, W is just a scalar multiplication of C. But is C positive or negative? Positive, right? Where C is positive. Here, if I would have made C negative, it would still stretch V, but now it just points it in the opposite direction, which we also discussed, right? So we also have that it's also a scalar multiplication of the vector C. But here, where C is negative. So what can we conclude from this discussion here about vectors being parallel? What do you think? They're just scalars of each other. They're scalar multiples of each other. So this is algebraic, but this is geometric, right? Just the way this was algebraic with geometric. So then we have that property as well now. A quick algebraic way to see if vectors are parallel is just to see if they're scalar multiples of each other. So two vectors are parallel if and only if they're scalar multiples of each other. So basically, we have an algebraic way of showing if they're going to be parallel. So here's the bonus. You don't have to do it right now. Try to prove it. Bonus there for you guys. Prove it. Let's say prove it. You can do that on your own. I can check it if you want. Let's see, where are we going with this? Whew. Okay, yeah, let's definitely take a break. Okay, but yeah, after this question.
How many components do they have to have in common in parallel? Just one or at least?
Great question. All of them. All of them, yeah, because remember, here, that's a good question. So, how can I tell if vectors are scalar multiples, right? Yeah, that's a good question. So, for example, let's say V, let's put some components there, and W are like that. And so then if W is a scalar multiple of V, then we have this going. This vector is now equal to C of V1, C of V2, C of V3. So a fast way that you could do this, kind of going off of what you're saying, is their components are proportional to one another. Meaning, if I divide this component by this component, the first component by the first component, what should it equal? C. And that should be the same thing if I multiply the second component by the second component. The third component by the third component. Right? So for example, sorry, that question like is getting me all excited. So hold on. So which vector is a scalar multiple to, let me make one up. 1, -2, and 3. No, let's not do 1. Let's do 5. Is it, let's say, vector W being let's see. This vector or this vector. All right, let me put the question mark here and remove these ones. Hopefully I did that right. So I want to see which of these two vectors is a scalar multiple to this one. Okay. One way to check is to see if they're proportional. So you can divide this first component by this first component. What's 15 divided by 5? 3. What's 6 divided by 2? 3. What's 7 divided by 3? It's definitely not 3, right? So that means that what? It's not, because if I was to multiply this vector by 3, by a scalar of 3, it would be 15, 6, but then it would not be 7. Okay. But now let's try this one. So I got 2 divided by 5 is just 2/5. But let's do 4/5 divided by 2. That's really 4/5 times 1/2, which is equal to 2/5. So that's matching so far, right? And then let's do 6/5 divided by 3. That's really 6/5 times what? Times 1/3, which is 2/5. So therefore, these are proportional to each other. This vector multiplied by 2/5 gives you this vector. So they're scalar. So that'll be a quick way that you can do it on your homework to see if they're scalar multiples of each other. What does that mean about geometrically these vectors? What's their relationship? Oh, here. They're parallel. They're parallel to one another. Okay? Does that help answer your question? Okay, guys, let's take a break. Come back at, let's do 7. 2:13. 2:13. Get like energy, because what we're about to do right now is a doozy. Okay, so pump yourselves up, do some jumping jacks, whatever you guys need. Oh, thank you. Oh yeah, if you came in a little late, please turn in your exercise set 1. Turn in your exercise set 1. Okay. Yeah. If you showed up a little late. All right, pause the recording. Resume the recording. All right. So I'll leave this here for now. All right, we got 2 things we're gonna do with dot products. One is the relationship that vectors have with lines and slopes. and then something called the vector projection. Okay? And I believe that'll do it for that section. The vector projection one we pick a while ago. All right. You need to do a bit of stretching between, don't worry about it, go for it. I think because the class lands like during lunchtime, I think it's like your body's like, a little like tired. Okay, this is not your textbook, but this is something that is very important when it comes to lines that we'll be using later on. So I want you guys to consider, let's say, a line with slope m equals a over b. Okay? Good algebra stuff you guys learned. Let's say the line shoots like that, x and y axis, and it has this slope right here, a over b. Okay. Now let's pick two random points on the line. Let's say this point and this point, so that we can make a vector out of it. Okay. So I get 2 points on the line, and then bam, I have this vector pointing down. Okay. Here's what I want you guys to help me with. Remember that a vector, don't write this part. We look at the component, right? The first component tells you what about the vector? That's called X component. The X component, but what did the X, what did the number of the X component tell you about how the vector is moving? How much it goes in the X direction. Right. And then the second one told you how much it moved in the Y direction. Now, if this line has a slope of a over b, how much change happened in the Y direction? A. Because remember, this is the change in Y over the change in X. Remember that from slopes? Rise over run. So then if the rise is A, then the Y value is changed by a value of A, and the X value is changed by a value of B, right? And so, therefore, this vector here has components what? Has components, how much change happened in the X direction? B. How much change happened in the Y direction? A. Good. But then I can use scalar multiplication and factor out a b. I can factor out a b from the vector. And then what am I left with when I do that? You're left with a 1, and then a over b. But what is a over b? It's the slope. It's the slope. So it's really just 1 over m. Okay? And so what I want you guys to notice in this is, this tells us that, that both vectors v and 1m, v is just a scalar multiple of the vector 1m. Right? You guys see that? Those are, and they're going to be parallel, right? Because of everything we just discussed. So are parallel. They're parallel to each other, but they're also parallel to the line. Recap that again. Sorry. So if a line has slope a over b, if I pick 2 points and I create some vector out of that, according to the slope, there should be a y change for the second component and a B change for the X component. And then through algebra, I saw that now vector V is a scalar multiple of vector 1n. But we just discussed before the break that if two vectors are scalar multiples of each other, then they're parallel. Okay? And because vector V is parallel to the line, because it lies on the points that are on the line, when vector V is parallel to the line, and now we have that vector 1n is parallel to V, then it must also be parallel. Okay. So what I'm gonna have you do, I'm gonna have you guys try this guy out to see how you're gonna use this property here. If you have a line with some random slope, then you can create a vector that's parallel to it with components 1 comma its slope. That's the moral of the story. Okay. If I give you a random line and it has a slope, then you can create a vector parallel to it that is 1 comma its slope. Okay? Okay, so with that, I want you guys to try this out with your groups. So find the acute angle between the lines 2x minus y equals 3 and 3x plus y is equal to 7. And then use vectors to do this. Okay? Try to do it using vectors. Find the acute angle between these two lines. Using what we discussed here and everything we've been doing in today's section. Definitely ask your group, work together. This one's not, it's not. Hence, use vectors. Okay. Since you know how to find angle between vectors. Okay, guys, what I want you to do right now is just check in with your group, stop what you're doing, check in with your group, and share your strategy with each other, okay? So I see different strategies. Just do a quick check-in. Quick check-in, guys. I can share your strategies.
No, I know what you said. I know what it is.
Oh. It would be the same, kind of like, you know, vector A will be. And vector U parallel, but if vector B. It'll be the same. So using like, just both vector B. One parallel. So you find a vector that is parallel.
Geometry, I swear.
A vector that's parallel to the other one.
Sure, yeah, I know.
So turn the.
Hey, but I passed, hey, I tell
I guess.
Yeah, really.
Yeah, action using the one, the vector is one.
Yeah, I had all just studying that. Because like, sometimes you do problems, but it was kind of big on there. Like, oh, yeah. We have it.
I got negative 5.
Oh, my God. Or like, you know, or like a triangle, like side, side, and you know, like, only five. How boards, I didn't. Oh, yeah, I don't think that.
So what do you think the relationship is between the angle between the lines and the angle between those two vectors that you found?
Yeah, but it's like. Knowing.
I just great. So these two vectors would have the same angle.
So when you yeah, so. Sign that in. Vector buffer there. Okay. Theories here. Yeah, those as vectors.
It's just.
So guys, just remember, here's the summary of this. So a line with slope m is parallel to a vector with components 1, n. Okay. So what's the slope of this line? If you rewrite, right, you get y by itself. Let's see, you move the 3, it'd be 2x minus 3, so the slope is 2. So if this line has slope 2, then there exists a vector parallel to the line with components 1, 2. Yeah. Isolate y here, move the 3x. The slope is what? -3. There exists a vector that's parallel to it with components 1 and -3. Correct. 1 and 2. Okay. Keep going. Just sharing that because some people we're not connecting this guy.
Yeah, I got
Okay, yeah.
It's gonna end up being. Oh. That's like one of like. The angle like this. Right? We have to-
Yeah.
Oh, no, that's not like.
One slope is.
Yeah.
Oh, yeah.
Low,
It's one load. If you think about the vector, it's one on the shot. But it's still a line, so it's close to. And so that's literally. The reason it's. It's gonna sit with slope is. Or the wide.
Oh, you got one good part. So what did it say? Find out.
Okay, I gave you 135. Okay,
Except it would be negative.
Teacher would put like formal, like, it's like, okay.
negative.
Like, give a simple.
Cause I had that too, but I.
You know, I come to school, so like, oh, okay.
And then you do the
Now,
second.
pretty cool, because you put on an angle, and then afterwards, it's not fall, it's supposed to be not, what did you do on the full, yeah, that's what I thought. No, that's all.
Negative one. Divided.
It was like you use everywhere around that.
But it's not a different state.
Well, think about the lines. The angle between them is gonna be an acute angle and obtuse.
We just do like 180 minus 1.
I'm trying to remind you, like, going, like, hey, this is how you.
And then that gives us 45.
By the way,
We all got. But it's not.
Because basically.
Angle between lines, there's always gonna be. It's always gonna be.
All right, guys, let's see. What'd you guys get? Getting 45. Let's see how that worked. So we call this guy here. Let me make sure I'm recording. Yeah. We call this B, call this W. The angle between B and W will be the same angle between the lines since they're parallel, right? So now it comes down to finding the angle between the vectors. And I saw most of you guys were using the theorem, right? Taking the dot product and then taking the magnitude. So then you guys take the dot product of this, it was giving you what? What's that, -6? -5. What did you guys help me out here? What did you get for the magnitude of V? √5, magnitude of W? √10. And so then you guys got, what is that, √50? Or, yeah, take out 25 and a 2, so that was 5√2. So then you got -1/√2. And then you bust out the calculator. So theta is going to be cosine inverse of -1/√2, which gave you 135. So then that tells you that the lines, here's 135, but the question's asking you for acute. So then what's that angle? 180 minus 135 gave you 45. Good. Question?
If we didn't specify the cube in question, would we write the angles?
Yeah, I guess it would say the angles, find the angles between them. Sweet, right? Useful. Okay. So the last thing we're going to discuss here, or actually any questions on this? We're going to use this again, okay, in the future. Okay, so the last thing I want to discuss is something called a vector projection. If you're in linear algebra, did you guys cover anything called projections in linear algebra? Maybe, probably not though, huh? Was it through, did you guys take the 3-week class that was in algebra? Damn, it's 3 weeks as beast mode. Okay, let's see. Vector projection.
Yeah.
Did you guys have like a test every other day?
Every day.
At the test, okay. Okay, so 2 tests in the final. Makes sense. No, they don't. They don't. But they do. Some linear algebra classes do teach something called projection, which is related to this. But I don't think that one. I don't think at DVC covers that. I haven't taught that one at DVC yet. Okay, guys. So here's basically what's going to happen. Okay. Let me give you the gist real fast. So if I have 2 vectors that are not perpendicular to themselves, they're just like this, right? There's a way that I can use 2 non-perpendicular vectors to create a perpendicular vector. Okay. And what it's going to come down to is where I guess, can you guys see maybe where there can be let's say I pick the black vector here. Can you guys see like kind of like this little perpendicular line that drops down here? So if I can find this vector here, then that's going to be perpendicular to this. So here's what we're going to do on the board. I have my 2 vectors. Imagine I have a flashlight right above them, and it casts this blue vector casts a shadow on this black vector, right? And that vector is going to cast a shadow right at the tip of it, right here. Is that cool? That's called a projection in math. I call them the flashlight shadow thing. Okay. So when you project this vector, projecting this vector onto the black vector is called a projection. So we're going to get its shadow that's going to be now this long. And then we're going to get this vector and subtract it with the blue one to give me the desired perpendicular vector. That's what we're going to do. Okay? But let's see how we're going to do that. How do I cast a shadow in math? So, given a vector V, we're going to find an orthogonal vector to it. Orthogonal vector to it. So I'm gonna define a couple things. Consider some other vector W. If you can, we're gonna write some stuff here. Draw like a picture somewhere around here in your notes. So I got my vector. Make it big too, okay? You're gonna label it a lot. Here's my vector V. And this is the power of this, what we're gonna do. I can then pick any vector. Let me do this one. W, and let's just say it's kind of like right here. All right, we're gonna define the shadow one, right? I'm gonna project W onto V to make that shadow vector that I told you guys about. So first bullet point here. So the vector projection of W onto V and this is how we're going to denote it. It's not the best notation, but it is what it is. We're going to write PROJ for projection. And then to specify that it's W casting a shadow on V, you're going to write V in small subscript and then W in big. So that you see it's W onto V. This guy is going to be parallel. I want you guys to notice that it's going to be parallel to V. Is that perpendicular I told you guys about? And then this right here is what we're going to call a projection vector. So, yeah. So now we want to get the orthogonal one, right? To do that, notice we're going to subtract W minus the projection vector gives you that desired orthogonal vector. W minus the projection goes from here to here, which is exactly going to be this vector that goes straight up like this. That has a different name. This is called the orthogonal projection. So the orthogonal projection of W onto V this one, we're going to denote it like this. Orth and then W onto V. By construction of how we're defining all this, that vector is the one that's going to be perpendicular to it. And the projection is parallel to V, but the orthogonal projection is perpendicular to V. So now the question is, oh, and to get this guy here, to get this one here, notice that what we're gonna have to do is we have to do W minus the projection vector. That's how we're gonna find this guy, by subtracting W minus the projection to give me the green. So therefore, in order to find that orthogonal vector, I need to find the projection. Now the question is, how the hell do I find the projection? So that's the question now, is how do I find that projection vector? Since that's the one we need. Our definitions. So here's what we're gonna do first. We're gonna define its magnitude first. Okay? Because do you see how this made a nice, a pretty little right triangle? We can use trigonometry to help us find this length. So we're first gonna define the length, the magnitude of that vector. So that's gonna be our starter. And that is the definition. And a hell of a definition, I apologize. Called the scalar, so let the scalar projection of W onto V, this one, this one is not ska, okay? It's comp for components of the vector. Okay, this is called scalar. Sometimes it's called the component projection, but your textbook calls it scalar. So this guy is going to be defined to be the sign, so that it's either positive or negative, magnitude of that projection. Slow down, just a whole bunch of stuff to write there. Okay, and so what we're gonna do is to find that magnitude here, we're gonna use V and W only to help us do that. And let's see how we're gonna do that. Fact. Boom. That component, that scalar projection, the way we're gonna find it is, it turns out to be the dot product of V with W divided by the magnitude, the polygon variable. Okay, sure. Why is that true? So let's prove it. We have the tools to do it. So notice, if I draw those vectors again, W, V, and then here I have the projection. This distance here is what we're defining to be this guy. Right?
That's what we're defining this to be. That distance there. This is a right angle. And there's an angle between those two vectors. Between V and W. Okay, there's an angle between them. How long is this hypotenuse of the prime? How long is that? If this is the vector W. It's just the magnitude of it. That length is just the magnitude. Yeah. But what I want you guys to see is if we use some trig here, okay? I use trig. We have the cosine of this angle is the scalar projection, which is supposed to represent some numerical value, over the hypotenuse, which is the magnitude of W. So with trig, we have this little ratio here. Yeah. So then isolate for the projection. And then, how did I keep it this way? Yeah. And so then therefore, I have the projection is the magnitude of W times cosine theta. Does that give me what I want? Is that what I'm proving? No. Okay. It's not, yeah, it's real. Okay. Let's use that theorem. So since from our theorem, we have that the relationship between this angle theta is the dot product of those two vectors. This is just from the theorem and the angle between them. It should be equal to this right here. Okay. How can we manipulate this to kind of use this?
You just plug in all that for cosine.
You can just plug all of this in for cosine. Yep. So let's see what happens if we do that. Oops. W. And then here we got magnitude of V, magnitude of W, and then what happens? Yep, these are just numbers, right? All these are scale. Everything here is a scalar. So this scalar cancels off with this scalar. And so therefore we have the projection vector is now just the dot product of the two vectors over the magnitude of V as we were doing. So, so doing this operation with V and W will produce that desired length. That we want. Okay? Sorry, this is a little. I didn't like how I wrote this here. Let me write it here for the next one. Can we use this part of the board? Okay. So now I have a way of computing that length. Just using V and W. But my goal though is to get the projection vector. Okay, that's my goal. My goal is I want to find what this guy's going to be. But remember, a vector has what two things? What are the two things that make up a vector? Magnitude and direction. This gives me the magnitude, right? So if I can get the magnitude and
if I can get the magnitude and a unit vector that points in the same direction, then I'm gonna have a unit vector pointing in the direction I want, and then I scale it by the scalar projection. You guys kind of see that? Okay. So, and here's an example of where the unit vector plays a role, where the unit vector just carries the direction, and I can scale it to how I want to move it. So I'm gonna have the magnitude that I want, and do a scalar multiplication of a unit vector parallel. The vector projection is parallel to V, so we want a unit vector parallel to V. Okay? This bad boy is this guy right here. That's how it's defined, right? It's the sign magnitude. The sign meaning that it might force it to point the same direction as V or point in the opposite direction. Okay? That's what that part is. But so this guy is going to be given by the component projection. Okay. How can I find a unit vector parallel to V? What can we do? Normalize it. Remember we learned about normalizing a vector? That means I'm going to get V, and I'm just going to divide it by its magnitude. That gives me a unit vector, which is what we learned last week. But from what we just proved here, to find this guy, I have to compute it this way. So then therefore now I have V dot W over the magnitude of V, and then V over its magnitude. Out of this numerator, this denominator, this numerator, this denominator, which is a vector? Which one represents a vector? Just the V one, right? Everything else is a scalar. So with scalars, I can like multiply things and move them around and stuff. So let's just multiply this with itself. Right? Like let's just bring this guy over here, so that it's this square. So then we have that the projection vector is just going to be V dot W over its magnitude squared. That big fat scalar times the vector V. This is the scalar that we want, so that it scales V exactly so that it's right below the tip of W. That's what we just found. Okay, I'll say that again. This right here is a scalar, the scalar we want, so that if I scale V, it shrinks it or it stretches it depending on how V looks like, so that the projection vector is directly below the tip of W. That's the scalar we want. Okay? So let me show you guys. I'll put this up in a little bit. Let me show you guys visually what's happening. And it's very abstract. So I have my vector. Here's V and W. See, notice it's in 3D space, just floating around. Okay. We're going to do an example right now where I have two vectors, V and W, with their actual components to help me find the projection vector, which is this guy right here. It's kind of, I'm sorry if it's a little, can you guys see the green? Yeah. Notice that it's right below the tip of the other guy. And then I'm going to subtract W with the projection vector to help me find the orthogonal vector that I'm desiring to find. And notice that it's true. The red orthogonal vector is perpendicular to the vector V. Cool? So that's what we're going to do. Let me see, does it let me? If I change W, look, this is going to be true regardless of what W looks like. even if W is pointing in the opposite direction. Let me stop right there. Oh, stop it. Even if W is pointing opposite of V, like it's pointing this way, that orthogonal vector is still going to be perpendicular to V. Okay, and the reason this definition says signed magnitude is because now it's moving the projection up in the opposite direction, so it's positive or negative. That's kind of what's happening. Okay, that would have been really hard to draw. Okay. What's this? Okay. So this one here is what you're going to be using in your home to find a vector projection. Say it again. You could totally use the conclusion. Right now, all the work we did is not what you had. It's just to show you mathematically why this equals that. But then the homework, you basically didn't use that. Okay? Or this one, because the homework might say find the component projection only, so that you only need to find that. You know, something that like I'm not gonna like require you to know proofs, no, because you haven't had any formal training in proofs. But me as the professor showing you this, need to convince you. But I am teaching Math 289 next semester, which is a brand new math class at BBC called Transition to Upper Division Math, which is Introduction to Proofs. So in that class, I'll be training students to prove. Yeah.
I think discrete mathematics also has a great CPR.
And discrete math also does that. You know, linear algebra has a lot of proofs, but they don't cover a curriculum that teaches you how to prove. The 195 covers that, and then 289 goes even further. Yeah, question. Calc 2. That's it. You guys being in this class, I'll give you guys more of a spiel later. I'm teaching it, and so I need to promote it. Especially if you're like a math major transferring, that's a really high important class. Okay, so I have a question for you guys. We have 15 minutes. Do you want to do a problem where you find the vector projection? Or do you want to take another field trip? I have one more field trip. It's called the Puma Center. No. Okay. I'm still gonna do it, but I won't do it today. Okay? Because some of you guys probably haven't been there, so we'll do it another time. We'll do it another time. Okay. I'm gonna have you guys do two things. Practice here. Actually, I'm gonna have you do three things. So I want you to find the see how much time do we have? Nope, I'm gonna have you do two things. Find the vector projection and orthogonal projection. Of W onto V. I'm gonna have to time this filter, that's another point. But here I'm actually going to give you the vector. So here W is a vector 4, 7, -4, and V is a vector 3, -1, and 1. So find the projection vector, and then, or the vector projection, and then find the orthogonal projection of those guys. Let me remind you that the orthogonal, I erased it, the orthogonal projection was W minus the projection. W is the big one. W is. So here's one thing you can use. See how W is being projected onto V? So V goes in the Y. And so that. Let me try something while you guys are working on that. Second. This way. Oh, I'm so stupid. Try it again. Whatever. Come on. There it is. Okay. If you finish early, what you could do is confirm that your orthogonal vector. How would you confirm that your orthogonal vector is orthogonal to V? How would you confirm it? Okay. What did you finish it? I guess you could look at this way.
What was your assessment? Okay, so and for the first second, it's 3 negative 1 1. So
That's one way of doing it.
3 squared. Yeah. So I think that's all. That's where we it's a long time already, it'll be a lot. So it's the going to. And so you could actually sign where you get every line. Yeah, so magnitude is basically. Oh, it's yeah. We got 41. Then it'll be 1.
You guys can check your work on the board.
Yes, so this goes like it's like yeah, very less than negative 111.
Oh,
That's negative, but yeah, these take this one, then subtract it by this, and then you get C.
I went up to like 80 pounds, so that's why you're explaining. Yeah.
And then now I'm just going to do some.
All right, guys, we have 3 minutes left. I just want to show you one quick thing. Oh wait, I already showed you guys the. Let's see.
Yeah.
And then if you want to confirm it, you just do dot for.
Actually, I'll save 3.4 to 12.4 to tomorrow, Thursday. Okay. Well, okay, guys. So hopefully this is what you got. How are you guys confirming this? You could use the dot product.
And then it's 0.
And then as long as they equal 0, then you're set. Okay. What's another way of doing it? Finding the angle between them and seeing that the angle should be 90. That's another one. Okay. All right. We'll end there, guys. So I don't try to squish anything in 2 minutes. We'll call it a day.
Switch all of them.
I was just gonna do an intro, like a motivational part.